Previous class we started discussing about the flying capacitor multi-level inverter. So in this the multi-level voltage can be obtained by multiple pre-charged capacitors. So these are the capacitors. So these are pre-charged to finite value, right? So based on the turning on and turning off of any one switch, right? If all four upper switches are on, so we know aware that so you'll get the 4E voltage. So if any one of the switches off, so you get 3E voltage. If two switches are off, 2E voltage, and if only one switch is on, E voltage, and if all the switches are off, you will get 0 voltage, right? So from this you obtain the voltage between A and this negative bus. So that voltage, you got a voltage of 5 level voltage starting from 0 to 4E. In case of line voltages, so which is varying from plus 4E to minus 4E. So we can also obtain the pole voltages. So this is the point, right? So where we can connect this, so assume this is the 0 voltage. So you can obtain the voltages plus 2E, minus 2E, E plus or minus E, 0 voltage. That also can be analyzed. So the drawback, so with this flying capacitor multi-level inverter is this pre-charged capacitors. So these capacitors we need to pre-charge to a certain value, right? So whenever we have some real power transfer is taking place, in that case this capacitor, so the stored energy in the capacitor may be reduced. So somehow we need to charge this again. So that means you require some charging mechanism and charging and discharging mechanism, or in other words, we need to regulate the voltage across the capacitor. Okay? So that is the one of the difficult tasks. So this flying capacitor, so this is the switching table for this flying capacitors. As we discussed this, only all four switches are on, any three are on, so any two, any one. So here all the switches are off. So we can observe some switching redundancy is there. In case of this flying capacitor, we have some switching redundancy is there. In case of cascade H bridge, so for that also we have some switching redundancy is there. So but we have topology for diode clamped multi-level inverter, so there is no switching redundancy. So you have only one possible way to obtain one particular level. So this is when compared to this when compared to diode clamp multi-level inverter, this flying capacitor is modular. So this is modular. So why it is known as modular? So means, so this is scalable. If you want to increase to higher levels, so that is known as modular topologies. For example, you have some 3-level inverter is there, right? For in your future, right, if you want some higher power demand is there, so in that if you want to enhance or if you want to increase the voltage and power level of the particular inverter, so we can easily scalable, maybe we can change it to 4 level, 5 level, something like that. For example, in case if you are talking about the cascade H bridge, somehow you identified that the 3 H bridges are enough for that initial time being, right? In future, right, if you assume that if you forecast that the power requirement is high, so in that case you can add 1 or 2 H bridges per phase, right? So this is known as scalability. So this scalability is possible so only when the structure is modular, right? When the structure is modular. So here the diode clamp is not a modular structure. So this diode clamp is not a modular structure. So why this diode clamp is not a modular structure? Because of this presence of this clamping diodes. If you want to extend, see here how much difference is there for 4 level to 5 level. So there is a lot of difference is there, right? But in case of cascade H bridge, so this is modular, the structure is modular. If you want to extend to higher levels, or if you want to extend, or if you want to increase the number of levels in future, so that can be possible. Whereas this flying capacitor, multi-level inverter, so if you look at this, so this is also modular. the structure is also modular. So how it will be modular means, so here, this is the structure here. So just we have structure something like this, right? So this is neutral point, this midpoint. So this is the one, right? So if you combine these things, that means if you pull these things in this direction, so if you pull this in this direction, right? So that means this is the first switch, and this is the second switch, and this is the third switch. Again, so this is the other switch, and this is this switch, and this is this switch. Okay. So that means we are folding this one across this axis, across this axis. So that, so it will be a modular one. So this can be a modular one. So that means this is, for example, this is charged to E voltage, and this is charged to 2E voltage, likewise. And here this will be your DC bus. So these three will form an upper switches, and these three will form a bottom switches. So this is known as, right, so this is known as multi-cell layout. So this can be represented as a multi-cell. The flying capacitor multi-level is modular when compared to this diode clamped, right? So, but here there is another drawback. So if you want to extend this one, so you have extend another modular. For example, this is the cell one, right? If you want to extend this one, so you need to insert so one more cell here, and this is E. So this is 2E. So next you have maybe 3E, likewise. That means the new one, so that's supposed to charge for 3U voltage. And moreover, this DC link is common to all the three phases, right? So when you talk about the modularity, right? So here, this diode clamped multi-level inverter is least modular, right? Whereas this flying capacitor multi-level inverter is modularity is medium. So whereas for cascade H bridge, so that means the modularity is high. So its modularity is very high. So come to its application. So especially in case of this flying capacitors. So one of the drawback is we need to pre-charge these capacitors, or we need to regulate these capacitors. So this is not an easy task. So this is particularly for 3 level or 4 level. So this is an easy thing. But if you increase the number of levels, so it will be a cumbersome process, right? So therefore, this is one of the main drawback. So therefore, whenever some real power transfer is taking place or something like that, right? So this is not particularly suitable. So this topology is not suitable for all kind of applications. So there is a specific applications where which is having a high number of applications. So that is traction drive. So traction drives, especially this drives, metro trains. So where you have frequent stoppages, we have stoppage for every 1 kilometer or 2 kilometer. For example, if you have Hyderabad Metro or New Delhi Metro, so we have frequent stoppages for every 1 kilometer or 2 kilometer. So in that, so whenever a train stops, right, the train drive, so we are aware that some regeneration is supposed to happen, right? So whenever there is a regenerative power with train stops, right, the simple thing is that they will interchange any two of the phases, so that the train will start, the motor will start rotating in the opposite direction. So once it reaches to standstill, right, so at that point the brakes will be applied. So that is how the energy is saved, right? Okay, so in this case, what will happen that, so if you have large number of capacitors, so the capacitors have a good thing that, so they instantly absorb the energy, right? So during this regeneration process, so if the induction motor, for example, most of the trains nowadays, early days, they used with series, DC series motors, right? Because of high initial torque. So now with the invention of this direct torque control, the thing is that the starting torque can be increased by using the advanced torque control schemes. So now we are using this induction motor drives. So with this induction motor drive, so that is usually fed by a two-level inverter or some multi-level inverter. If the inverter is a flying capacitor multi-level inverter, so because of this presence of this large value, large capacitors, so the excess energy, so that is initially charged, initially stored in these capacitors, right? And this is slowly transferred to the source. So that means the regenerative efficiency is increased if you are using a flying capacitor multi-level inverter. So this is particularly useful in case of applications like traction drive. So especially if you are aware that in metro applications, one of the leading manufacturer is Alstom. Right. So all this metro, our trains, especially Hyderabad or New Delhi, or it may be in Mumbai, so that is procured, those motor drives or the locomotives are procured from this Alstom only. So inside this, you may find 3-level or 4-level flying capacitor multi-level inverter, so which is coupled to a induction motor drive. So that is the only advantage, or that is the only predominant application. So with this flying capacitor multi-level inverter. So in most of the other cases, we'll try to avoid these as much as possible. So next thing is, how the input for a flying capacitor multi-level inverter will look like. So this thing is, right. So we have two parts here. So this is usually known as front end, right? So this is the actual inverter, which is coupled to some motor drive or some anything, right? Okay. So this is how, this one is DC link. So this is how the DC link is formed in case of real power applications. So as we already discussed when we are discussing the cascade H bridge, okay, this front end is required only so when you require a real power transfer. In case of applications like STATCOMs, where the real power requirement is not necessary, so in that case we will replace with capacitors only. So here, so this will replace with 3 capacitors. This is a 4-level, right? So we will replace with 4 capacitors. Okay. So this is how these 3 sources, this is 3 isolated DC sources. So this is how it is generated. Okay. So this is a multipulse converter again. Multipulse converter. So this is 18 pulse multipulse converter. We'll discuss in later classes. Right. So this is how exactly, so this is generated. So this is connected to one 6 pulse converter. So this is connected to another 6 pulse converter, and this one is connected to another 6 pulse converter, so that you have 3 isolated DC sources. So where you have this 18 pulse converter is there. Okay. Right. So next we have this hybrid concept, hybrid multi-level inverters. So if you notice that, so this is a cascade H bridge inverter. Okay? So this is a cascade H bridge inverter. So in case of cascade H bridge inverter, so this is supposed to be a H bridge, right? So this is supposed to be H bridge. So instead of H bridge, if you notice that, so this is a single phase diode clamped multi-level inverter. You can see here, this is a single phase diode clamped multi-level inverter. Instead of having a single phase H bridge, we have this single phase diode clamped multi-level inverter. So this itself, right? So this is producing, so this is how many levels it will produce. You have E voltage, right? This is a single phase, so it will produce E, 0 and minus E. Okay. So no, this will produce, so this voltage, right? So here, So how much? So what voltage it will produce between A and N? So this will produce, right? So this entire thing, so if it is coupled here, right? So that means this voltage may be produced from 2E 0 to minus 2E. So you have plus 2E here and minus 2E here. Okay. So instead of a single phase HP, so we have this diode clamped multi-level inverter. So that is how it is used for increasing the number of levels. So this is known as hybrid MLI. So we'll discuss more in later classes. Right? We'll discuss this. So we'll come back to these things. Right. So next we have comparison of these multi-level converters. Comparison of these multi-level converters. So you have one side you have neutral point clamp, you have flying capacitor, you have SSBC. So this is also known as cascade H bridge. Okay. The first thing is the main switching devices. So main switching devices. So how many main switching devices? We already discussed that. In case of neutral point clamped or in case of diode clamped multi-level inverters. So here require 2 into m minus 1 number of switches. So here also you require 2 into m minus 1 switches. So here also you require 2 into m minus 1 switches. So this is anti-parallel diodes. If you have 2 into m minus switches, the same number of anti-parallel diodes is required. Same number of anti-parallel required. So clamping diodes, as we discussed in one class, in case of diode clamp, you require m minus 1 into m minus 2 per phase. So all these things are per phase. Okay, so far all these things are per phase. Right. Clamping diodes are required. In case of flying capacitor topology, so no clamping diodes is required. In case of cascade H bridge also, so no clamping diodes are not required. But in case of flying capacitor, right? So here this number is 0, no flying capacitors are required. So whereas here you require m minus 1 into m minus 2 by 2 number of clamping diodes are required. No, flying capacitors are required. So this number, right? So this number is, so this is the number, so m minus 1 into m minus 2 by 2. So this is 6, right? So m minus 1 into m minus 2 by 2. So you have 5 levels, right? 4 into 3 by 2. So that means 6 is required. This is 6 per phase. You require 6 per phase. Similarly for CHB, so flying capacitors are not required. Flying capacitors are not required. And in case of DC bus capacitors, so for M level, you require M minus 1 DC bus capacitors. In case of flying capacitor, you require M minus 1 DC capacitors. So whereas here, so this is M minus 1 by 2, right? So in case of CHB, for 5 level, okay, so how many DC, how many you require? So it is M minus 1 by 2. So that means you require 2 H bridges. So this is, you require 2 bridges per phase. Okay, you require 2 bridges per phase. So meaning is, so this entire thing, this is common to all 3 phases. This is common to all 3 phases. So this is also common to all 3 phases. So whereas this one, so this is per phase requirement. So this is per phase requirement. If you want 3 phase, so you need to multiply this one with 3. So all these things are per phase. So this is also per phase. So this is also per phase. So this is also per phase. And this is also per phase. So now tell me, so which require least number of components? So which one require least number of components? For example, in case of 5 level, so which require least number of components?
Sir, cascade.
Which requires least number of components. So this cascade edge bridge should usually require least number of components, right? The neutral point clamp, you require this much of clamping diodes. In case of flying capacitors, you require so this much of flying capacitors, right? Okay. So here only the thing is that you require 4 DC sources, isolated DC sources. So here you require 4 isolated DC sources, but you require 6 isolated DC sources. Okay. On an overall note, so the CHP requires less number of components. So when compared to this 5 level CHB, when compared to 5 level this flying capacitor or this neutral point clamp. In case of 3 level, in case of 3 level, so in case of 3 level, right? So more or less all require same number of components. All require same number of components. For example, in case of this clamp, you require 6 additional diodes. Okay. So how many you require? 3 DC sources, 3 isolated DC sources, but you require only 2 DC sources. This also you require 2 DC sources, and this one you may require this 3 level, right? So you require only 1. So that means this is 1 or 1 into 3. So that means 3 flying capacitors you required, right? So this is for all 3 phases. The thing is that, right, you require 1 isolated DC source and you require 6 additional diodes. So there will be some trade-off, right? So that means the cost of these things more or less same. If we precisely calculate that, so in this case, this neutral point clamp at this flying capacitor cost will be less. So that means the thing is that for less than for 3 level or 4 level, 3 or 4 level case, this neutral point clamp, right, cost will be less, or this flying capacitor cost is less when compared to the CHB. When compared to the CHB, whereas for greater than 5 level, the cost of the CHB is less. Okay. So this is overall comparison of these multi-level inverters. So we have first point. So one is the specific requirement. The first one is specific requirement. For diode clamp, you require clamping diodes. In case of flying capacitors, you require additional capacitors and their initialization. So meaning of initialization is, so their pre-charge of this flying capacitors. In case of cascade edge bridge, so you have this isolated DC sources. You require isolated DC sources. So next you have modularity. So as we discussed, this diode clamp is low, less modularity is low when compared to, so this is for flying capacitor, this is high, but whereas cascade edge bridge, so this is very high. And design and implementation complexity, design and implementation complexity. So in case of flying capacitor, in case of diode clamp, so the design is easy, right? Somewhat low. For flying capacitor, it is medium, right? So in case of cascade edge bridge, so this is least. The design implementation is least, right? So in case of cascade edge bridge, so there are 2 possibilities, okay? So one is with real power transfer and another one is reactive power transfer. In case of real power transfer applications, so additionally you require front end, right? So which you require a multipulse rectifier. In case of reactive compensation or applications like grid integration, so in this case, either you require capacitors or PV sources or batteries. Okay. So here, so this approach, right? So this approach is least. So that means cost effective. So the cost of this is also less and the complexity is also very less. But whereas you require front-end converter, this multipulse converter, so this kind of arrangement, so this is highly complex, right? So this is highly complex and moreover, right, this cost is also very high. So cost is high and complexity is also high. Understood? So now come to our discussion. We have design and implementation complexity. So this is least. So in case of this thing, so reactive power reactive power control or grid integration. Okay, and it is highly complex, right? So it is highly complex in case of multipulse converter arrangement or in case of real power transfer. Understood? So next you have control concerns. Control concerns. In case of diode clamped multi-level inverters, as we are aware that, so there is no switching redundancies. So there is no switching redundancies. So therefore the thing is that capacitors balance, right? The DC link balance. So that is one of the complex thing, right? So in case of flying capacitor, so voltage setup. So that means regulation of flying capacitors voltage. So that is the complex thing. Okay, in case of cascade edge bridge, the power sharing among the isolated DC sources, so that one is the complex thing. So everyone is having their own disadvantage when come to this control concern. In case of diode clamped, so voltage balance among the two or among the DC sources, so that is complex. In case of flying capacitor, precharging and maintaining the voltage across the flying capacitor, so that is complex. In case of CHB, the power sharing among the isolated DC sources or among the PV cells or among the batteries, so that is the complex thing. So next one is fault tolerance. As we discussed that if the fault is occurring or if a fault is happening, so we need to reconfigure the inverter such that it may be operated at its full power or it may be operated at its reduced power, right? So in case of diode clamp, so it is difficult. So why it is difficult? The thing is that we cannot reconfigure the diode clamped multi-level inverter, so because it is not having any switching redundancies. In case of this flying capacitor, so this is somewhat easy because of the presence of modulator. This is also in case of this cascade edge bridge also, so this is easy. So next we have applications. So we have applications. In case of diode clamp, so this is suitable custom power devices, right? So this is custom power devices. It is known as CPDs. Okay. If you are aware that facts, so facts is for transmission lines. Facts is for transmission lines, right? And CPDs is for distribution systems. In case of facts, by using these facts, we can increase the power transfer capability. We can have reactive power compensation and voltage regulation at a particular bus. So those things can be possible with facts. That means control of active and reactive power in a transmission line. So those things can be possible. So in case of CPDs, so this is custom power devices. So this is also look like a facts device, but So this is at lower voltage levels, and their objectives is also different. So here this is distribution systems. So we have, this is primarily targeted to improve the power quality. Right. It may be used to reduce the current related harmonics, voltage related harmonics, reactive power compensation, right? Power factor improvement, or if the load is unbalanced, or we can, if the load is unbalanced, if the source was unbalanced, so that unbalanced compensation, or the if the neutral current is there, so neutral current compensation, so all those things can be used. Or if you have a voltage sag is there or voltage swell is there, so all the things can be compensated. So that means predominant or primarily, so it will improve the power quality. I think you might have studied the subject power quality, right? So those are known as custom power devices. Okay. So we have this adjustable speed drives. ASD means adjustable speed drives, that is known as motor drives. Motor drives, conveyors, marine applications, and regenerative applications such as mining and renewable energy. So these are the applications of this diode clamped multi-level inverter. So come to this flying capacitor. So we have this adjustable speed drives and medium voltage traction drives. As we discussed that in case of traction drives, so this is particularly suitable. Okay. So come to this CHB. CHB is especially suitable for FACTS. Okay. So why it is FACTS? In case of FACTS, it is connected to the transmission lines, right? So transmission lines, the voltage rating is very high. So therefore, the CHB is a suitable choice. So this is also used for custom power devices, high power adjustable speed drives, high power adjustable speed drives. The thing there, for adjustable speed drives or for motor drives, you must have a real power transfer. You must have a real power transfer. Again, if you have real power transfer, you require a multiples arrangement. So that's why if you have a high power transfer in the range of 100 kilowatt or 100 megawatt range, in case of steel mills, for example, especially steel mills, you require a motor which is having 100 megawatt range. You require a motor 100 megawatt range. For also you require for lift irrigation projects. Lift irrigation projects, right? For projects like, for example, we have Kaleshwaram project is there, right? That is lift irrigation project. So where you have a motors which is having a capacity of 30 megawatt, and we have some motors with 50 megawatt range. Okay. So all these motors, so it is coupled to a cascade H bridge inverter. So motors, if you want some control, so that is connected to a cascade H bridge converter. So this is especially suitable for steel mills, right? And applications like lift irrigation projects. So in that case, the motor size or the motor capacity is very high. Or in case of underground excavation, right? So there is also, you require a high capacity motor. So all those things we normally prefer cascade edge bridge. So whenever we require some control of speed or control of torque or anything. Okay. So next we have electric and hybrid vehicles, electric and hybrid electric vehicles. So for electric vehicle also, so the CHB is one of the suitable choice. So we have photovoltaic power conversion. So that is also one of the, it's a good area for CHB. You have this uninterruptible power supplies, and magnetic image resonance, MRI scanning, right? You know, you're aware that MRI scanning, right? So this is used to identify, so MRI scanning, so that we'll use it to identify if our blood is having some magnetic properties, right? So if you are, if it is magnetized, So you can see that whenever there is a blood clots, or if some of the parts, if there is the blood is not flowing to the some of the parts, so that can be identified. Okay. So for that, okay. So for that, you require high voltage, because that is operating at, for example, if MRI machines are operating at 1.5 Tesla magnetic field or 2 Tesla magnetic field, so that is very high. So for that, you require a high voltage. So to attain that high voltage, so which is obtained from a CHP. Similarly, for X-ray machines also, if you have X-ray machines, the voltage of that X-ray machines is usually 75 kilovolts. To attain this much of high voltage, we require all these kind of CHP cascade H bridge converters are required. Some of the medical applications where you require high voltage, so in that also we normally prefer to use this cascade H bridge. Okay. So next we have, so this is the applications of this CHB. So come to the cost, as we already discussed that for low 3-level or 4-level, so this diode clamp multi-level inverter is cheaper. In case of flying capacitors, so this is also somewhat cheaper in case of 3-level or 4-level. Okay. In case of CHB, right, as we already discussed that for real power transfer, so it's wherever with the real if front end is not required or multipulse converter is not required, so in that case, so this is very cheap. So this is for transformerless applications. Okay. So wherever you require a high input transformer application is required, so that cost will be high. So the CHB, in case of motor drives, the conclusion is in case of motor drives, its cost is very high. But in case of applications like FACTS, custom power devices, electric vehicles, or any applications, so in that case, its cost will be very low. So available commercial ratings. So their commercial ratings. So what is the voltage level? See, in case of this diode clamps, so these are available from 2.3 to 6.6 kV range, and its voltage is from 3.7 to some few MVS are available. In case of this flying capacitors, so these are usually operated 2.3 to 4.16 kV, so with a range from 2.24 to a few MVS. Right. So whereas CHB, so this is usually for higher voltages, we have 13.8 kV. So with the power range up to 120 mega MVA. So here you can see that 120 MVA inverters are available. So this is about the comparison of these different multi-level inverter topologies. So usually for low power applications, right, for low power or low voltage applications, so we normally prefer this diode clamp multi-level inverters. For high power applications or high voltage applications, the CHB is preferred. Okay. So next we have, so this is the market overview of our different manufacturers. So we have different manufacturers are there. So this is ABB. So this is the convert team. So this is for Siemens, and this is for GE. This is Indie Drive. So these are different manufacturers we have. So this convert team, so now it is moved to APC, American Power Supply. Okay, so this is 3-level neutral point clamped. Okay. So 3-level neutral point clamped. So every manufacturer, so it is coming with some product name. So this is ACS 1000, this is ACS 6000. So this is one of the popular power converter, this ACS 6000. Most of the almost 50% of the industries they're preferring this one, ACS 6000 drive. So we have this voltage and this current ratings are there. So this is a semiconductor switch that is used IGCT. Okay, and these are the different manufacturers, so that producing this neutral point clamped, 3-level neutral point clamped, and the switch technology, so that they are using. So next we have this 3-level active neutral point clamped. So this is actually we're not discussed. We'll discuss maybe in the next 1 or 2 classes. Okay, right. So this is another manufactured by ABB. So next we have this Allstorm. You can see here this Allstorm. So this is flying capacitor. So this is the only one that is manufacturing this flying capacitor. So that is Alstom. This is VDM 6000. In most of the metro trains drives, this is using. Okay. So this is on the main range of 8 megawatt range. So here the medium voltage IGBTs are used. MV IGBT means medium voltage IGBT. So we have Siemens. So we have Cascade Edge bridge. Again for Cascade Edge bridge, different manufacturers are there. Siemens, Hitachi, LS India Systems, and we have Schneider, and we have Rockstring, and we have Rockwell and Rockwell Automation. So these are the popular manufacturers. Okay. So this is the switch technology you can use. You can see the voltage, the power rating is also somewhat high. So this is modular multi-layer converters. This is not required. We will discuss in the later classes. This is HNPC, okay, hybrid NPC. We have seen this, right? In case of instead of H bridge, we have neutral point clamped, single phase neutral point clamped, right? So that is we have ABB, and this is also GE is also manufacturing that one. Okay, this is the one we are talking about. This is the one. This is 5-level HNPC, hybrid neutral point clamped. Okay, so these are the different market overview of this medium voltage drives. So different manufacturers. So any questions? You have any questions? Yes.
Sir, electric vehicle is a driver.
Hmm.
Electric vehicle.
Yeah, electric vehicle.
That is that is also type of driver, sir.
No, that is also type of drive only. Electric vehicle is also type of drive. This is the one we shown, right? This is an electric vehicle if you use a CHP. Everything is same. The thing is that the power is obtained from the batteries. That's all. Okay. So instead of having a so normal motor is rotating in right. So rotating. So that rotating is converted into linear motion by using that crankshaft.
Yes. Sir, on CHP side, we have multiples converter for this.
For this is not required, no?
Fronted.
This is not required for this because we have batteries are there, right? Okay. For this, no, multiples converters are not required. In next class, we'll discuss the multiples converters. Okay, we'll stop here. In next class, we'll discuss the PWM schemes, or either we'll start the PWM schemes or we'll start the multiples converters.